Morning.
Good morning, Niklas.
Now my camera's working.
Can you hear me?
Barely. But
No?
yeah, better. Quality's not normal, or not
Okay.
what it normally is, but it's enough to understand you.
Let's just wait for another couple of minutes.
Okay.
You guys started to put up the slides, etc.
Okay. Is there. Hi, Dr. Wang.
Good morning, class. Are we waiting for someone else?
No.
You say no?
No. Dr. Atwood won't join us today.
Okay. So then I'll begin.
I guess so.
All right. I'm gonna make sure my chair's right and. Oh, and if you're going to mention time, don't worry about that. I have multiple monitors, so
Okay.
it was
That's
open.
great. Yeah, that's good.
Hello, my name is Niklas
Um,
Byriel. Oh,
yeah, just like an official introduction before you get started. I just want to, because we have a committee, so I just want to formally introduce you, who you are, and as your primary advisor.
okay.
Although I think Dr. Wang knows you very well. So I'm very glad that today we'll have Niklas Byriel to present his honors thesis, flight simulation route generator. Niklas has been working very hard during I think starting 8 months ago on this project with his original idea being how to efficiently collect the data and show the data for flight AVs, right? If I'm right. And starting then, he started to do some literature search and finally finalize the research problem he's trying to solve. And then during last semester, Nicholas and I were working on this senior project. In the meanwhile, he's also taking my big data course on the similar project. So here today, he's going to present this work as a joint project for two courses, DS 495 and DS 420, the big data course. All right, so now it's time for you, Nicholas. You can just take it over.
All right. Hello, my name is Niklas Byriel. I use they, them pronouns, and I created a flight simulation route generator. Oops, come on. So it's no secret to anyone I talk to often that I absolutely love flight simulation. I fly all across the world in several different types of airplanes in a simulator called X-Plane 11. And I've spent almost 1,500 hours doing this over the past couple of years. However, given a world of possibilities, I sometimes can't decide where to fly to. So in the spring, I asked some friends to suggest airports. This list on the right is that list where I added some of my own airports that are famous for having difficult approaches. And I gave myself the challenge to fly between all of them using only real-world routes. So based on this, I ended up wanting to create two route generators, one with these real-world routes, and the other which I called routes by range. So before this generator, how do you find the best routes? So I used, for an example here, I used the leg between Paro, Bhutan to Wuhan, China. So I started by going to ticket searching websites, and I came across what I dubbed the 2020 effect. So as you can see from these screenshots, both Google Flights and kayak.com showed up no flights found as for between these two airports. A couple months ago, they did show some suggestions, but as flight schedules have decreased, this is less likely to find a route. Even when it does work, however, this solution is optimized for passengers. So this optimizes the cheapest tickets, the tickets that take the least time, which includes layovers. But what I want for flight simulation is the shortest route based on distance. The other thing I used for this is Wikipedia. So each Wikipedia page has a section called Airlines and Destinations. So the screenshot in the middle is a screenshot of Paro Airport's destinations. As you can see, Bhutan Airlines and Druk Air both fly there, each to a handful of destinations. So this also requires a bit of geographical knowledge, which I'll admit my Southeast Asian geography is not as good as it is in a region I've heavily studied like Europe. So I decided to look at Bangkok as a stopover point to Wuhan. So I clicked on Bangkok's page, and what showed up was this giant bar on the right side of the screen. There are 100 airlines that fly into Bangkok. It's zoomed out so far that I can't even read it at this point. But using some aviation knowledge, you can assume, for example, that Delta Airlines is not going to fly between Bangkok and Wuhan because they're from the United States. I was able to find China Eastern Airlines, screenshot at the bottom, which flies directly from Bangkok to Wuhan. And this route is 2,400 nautical miles. So once I got the generator running, I tested the same routes, and it suggested a route from Paro that stops in Dhaka, Bangladesh, then another stopover in Guangzhou, China, and finally to Wuhan. And this route is 1,900 nautical miles, which saves 500 nautical miles, which is about an hour of flying time. So if that can save this for multiple routes, that is significant. The other generator, the routes by range generator, as I called it, breaks a long route into multiple flights. So this generates stopover airports in the middle of a trip, which is useful in the example of this airplane. The one pictured here is a 757-300, which I very much enjoy flying in my flight simulator. So it has an aircraft range of 3,500 nautical miles, but let's take for an example the route between Singapore and Los Angeles, which is 7,550 nautical miles. This airplane obviously can't fly if it doesn't have gasoline, so it has to stop. So here's comparing a hand-generated route, which was the method I would use for this beforehand, to a computer-generated route. My hand-generated route stops in Tokyo and Anchorage between that, and that's a total distance of 7,900 nautical miles, while the generated route saves 250 nautical miles by stopping in Memonbetsu, I believe that's in Japan, and Erickson Air Station, which is on one of those islands at the tip of Alaska. This is, however, an even more useful tool for small planes. So take, for example, that same trip, except this time flown by a Cessna 172, which has a maximum range of 600 nautical miles. As you can see from this screenshot on the left of the generator, it takes at least 13 stops, and that's mapped on the right on Google Earth. And this could take me over an hour to find if I was searching for it manually. So the design of this project, just generally speaking, it is a web app. So that means I use HTML and JavaScript, which runs asynchronous scripts on the front end. And that communicates using HTTP requests and HTML and JSON responses to a web server implemented in Python Flask, which is running on Ubuntu, which runs on my computer in a Windows subsystem. This connects to a MySQL database, which has the data. So for this, there are 4 data sets required. I was looking at some of the more common data sources, and I sent an email to FlightRadar24 asking how much they charged. They responded saying, we do have a minimum offer value of 950 euros, which is slightly above my budget of 0. So I ended up finding the 4 data sets from 3 different sources. The airplanes data set, which has the airplane codes and the airplane names, I found from a website called Aviation Codes Central, and running some JavaScript on my web browser's console, I managed to turn that into a JSON object, which was pasted into a text file and from there imported into the database. The airports dataset I used from a company called Navigraph, which gives out or which sells subscriptions for flight data that can be used in flight simulation. So the Flights Factor 757 is one of the airplanes I like flying on the simulator. And one of the versions of the data for that has an airports.txt, which gives me all the relevant information about airports. For airlines and routes, I used a website called openflights.org that gives all four of these data sets for free. But I found that their airplanes and airports data sets were missing some pretty big airports and airplanes that I was trying to test with. The only problem with these data sets is that the routes data set is from 2014. I couldn't find a free data set that has as much data that is newer than that. So while this does mean that some of the routes are going to be outdated and the generator does end up generating routes flown with US Airways, which was bought by American Airlines in 2015, it still shows that the system works even with the older data set, because updating the data set would just have different routes to search with. So let's go over the algorithms a bit. So the search by range algorithm recursively searches for the next stop. So this starts at the departure airport, and then from there recursively finds a path to the destination. At each stop, it uses a MySQL query to generate a list of 100 airports that are within range. And this list is sorted by those that are farthest away from the departure airport. And this is all calculated within the SQL query. The screenshot is here, but don't worry about reading that because the next slide is going to show the actual equation. This is just to show how ridiculously long the calculation looks. So the resulting list is then sorted by the distance it is away from the final destination. And then that sorted list is iterated over. And if an airport in that list is already in the route, or if the route doubles back on itself, that airport is skipped and it just continues to the next one. And from there, it finds the airport closest to the final destination. And from there, it recursively generates the next leg of the journey. So distance calculation can't be done using the normal Cartesian distance equation that we're used to. For this, you have to use great circle distance because of the latitude and longitude coordinate system that the Earth uses, and the fact that it's a sphere. This formula was found by Thaddeus Vincenti, and just to make it easier to read here, delta lambda is the difference of longitudes, delta phi is the distance of latitudes, and delta sigma is the angle between the 2 points. So using this angle, you can multiply it by the diameter of the Earth to find the distance between the 2 points over the surface of the Earth. And for this purpose, I use the Earth radius being 3,443.9 nautical miles, nautical miles being the unit most used for distances in aviation. So here's an example of a route initially found by this algorithm. This is the example of Los Angeles to Honolulu, which I found to be one of the more challenging test cases initially, which was due to the fact that the best flight between Los Angeles and Honolulu is, of course, the straight flight, and there's no land between those two, and they're 2,000 nautical miles away. So using an airplane range of 1,300 nautical miles, the generator has to search around by going first away from Honolulu. So as you can see, based on this Google Earth mapping of the initial route, it is obviously not optimal. You don't want to go inland into the United States if you just want to fly around the Pacific. So instead of improving the algorithm, I decided to add on a couple optimizers that cut down on this. So the first one I called the cut optimizer. What this does, it calculates the distance between every pair of airports. And if that distance is less than the airplane's range, any airports that occur between them are just straight up cut out of the route. So this screenshot here is running the cut optimizer over that route from the last slide. And as you can tell, this already eliminates every instance of looping back and going back toward the departure. But this is, of course, not a perfect route yet. So I have a second optimizer, which I call the generate optimizer, and it generates new routes between every pair of airports that are on the route. Because the initial algorithm prioritizes airports that are far away from the departure airport, I have this running over the reverse route, which I hope reverses that bias a little bit. This, as you can see from this screenshot, comparing the two, I'm going to go back. Visually, the route does look a bit shorter. And this optimizer, since it generates a lot of routes, also runs significantly longer than the cut optimizer, which is why this one runs second. So the cut optimizer runs or cuts out a lot of the airports so that this one doesn't have to run over as many airports. This one, this optimizer, I lost my train of thought. The other algorithm, which is the search by route algorithm, is based on the A-star optimization of Dijkstra's shortest path algorithm. So the way I have this implemented, I start by creating a list of airports that have already been visited by the system. I initially populate this with only the destination airport, even though it hasn't been visited yet. And each entry in this list also saves the shortest route to that destination. Next, I create a list that I use roughly as a queue, which is a list of airports that are next going to be visited by the system. This one's initially populated with the origin airports so that route calculation starts from the origin. Also here, I create a variable that saves the optimal route length, which I have initialized to ridiculously high, starting at 10 to the 12th minus 1, which is significantly longer than any airplane can fly around Earth even multiple times. From there, I enter a loop that runs while the queue is populated. So in that loop, I start by calculating the route length from the departure to the current stop. So the current stop is the airport that is at the beginning of that queue. And if the distance between the departure and the current stop is longer than the value saved in as the optimal length, that is just removed from the queue, ignored, and the loop is restarted. The next check is to see if the airport has been visited yet. So it does this by checking that airport list. And then it compares if the route that is found through the queue is shorter than the route found in the airport list. If this is the case, the airport list entry is updated, and either way, it's removed off the front of the queue and the loop is restarted. If neither of these happens, the current airport is added to the airport list, and a series of MySQL queries are run to find the available routes, and then those are added onto the end of the queue. There is also an optimization that runs after this, and this one only runs if no optimal route has been found yet. So if the optimal route is still the default value, that means that there hasn't been a route between the origin and destination airports. And this only runs for the first 50 iterations, which happens because, and so inside the first 50 iterations, it sorts the queue by the distance from the destination. So this encourages if the shortest route roughly follows the straight line between the two airports, this optimization encourages that route to be found. In some cases, this doesn't work, and the reason that it's limited to only 50 iterations is because if the route doesn't follow the shortest line, then this optimization is going to have the opposite effect, making it significantly longer to find a route. After the queue is emptied, the route is returned, or the route that is saved in the destination airport object is returned. So how well do these algorithms work? Well, searching by range can find almost any result in 20 seconds. Some outliers do take longer. The longest I've found recently is, I think, a minute, which is short airplane range over a long route. But I also feel like the algorithm isn't perfect, though without another source to test this against, this is mostly a feeling than based on evidence. That being said, while working on this presentation, I did find a couple optimizations that I could make. And this algorithm, as I mentioned earlier, is biased towards using airports that are far from the origin. this is why the generator optimizer runs over the reverse route. And of course, not every possible route can be generated because there are almost 8,000 airports in the database. So that just can't be run for processing time to generate an edge between every two of those. The other algorithm takes a long time to run. The more aircraft types are selected, the longer it takes to generate. But the algorithm does seem accurate. Again, this one's hard to double check with outdated data because no ticket booking website is going to give me a route that can only be flown in 2014 and not in 2020 or 2021. So I do plan on making some optimizations to this, the first one being caching. Each individual SQL query is very fast, but there are many SQL queries run. Each distance calculation, for example, sends 2 queries asking for the locations of the airports. I also want to improve the search by range algorithm to get what I consider a more guaranteed result. And I'm trying to look for an algorithm that might calculate or that might generate the route based on an airport's distance from the shortest line between the points rather than distance from the origin airport. I also want to add a feature where I can input a list of destinations that then generates a Hamiltonian circuit between those, which means that it starts and ends at the same airport, and each airport is only visited once. I also need better data, and one way I've thought about doing this is using a Wikipedia crawler, which Wikipedia doesn't have all the information I need, but it does have a lot. And I tried to implement this, but unfortunately, Wikipedia, though it looks standard, there are a lot of outliers to their pages. So not every page is structured even similarly. So now it's time for a demonstration. So if I could get a suggestion of a departure airport and an arrival airport, which are preferably on different continents, I'm going to show a route being generated between those two. These suggestions can come in the form of cities, airport names, or airport codes. And I need to change over to my web browser for this.
Dr. Lee, I think you were muted.
Yeah, I'm interested to see like some city in Florida to maybe Hong Kong.
Sure. So I'm going to start by doing routes by range. The departure airport, I'm going to say Miami, and the arrival, Hong Kong. Luckily, I know these airport codes because I've flown to both of them a lot in my simulator. I'm going to give the airplane a 2,000-mile range and a 5,000-foot minimum runway. So this is running. I can see I have the console open on another monitor, and this tells me at what stage it's at. It's currently running the predictions. So on the left is the sidebar. If you uncheck one of these airports and press update, it generates a new route that doesn't have that airport in it. The right sidebar is the other project Dr. Lee mentioned for the big data class. This uses machine learning models to predict based on the weather at destination column, where delays, diversions, and flight cancellations are likely. The actual middle portion is the actual route. So this breaks it up. You start from Miami to fly to KSEF airport, which is 115 miles away. Then to this airport, just to check. Do you see my mouse pointer?
Yep.
Okay. That flies to this airport in Canada. That crosses across to this one in Russia. Fly further south in Russia, and then down to Hong Kong. It has
K
also
is
the route
for
distances.
US, right?
K is yes.
Okay.
There is a rough scheme to airport codes. Well, a pretty definite scheme. An airport that starts with K is always in the US. If it starts with C, it's in
Canada.
Yes, Canada. If it starts with U, it's in Russia. I think VH is specifically for Hong Kong. V is a couple countries down in that area. So I know Macau is VM. So I'm going to press update here. I unchecked that Canadian airport. So it's going to generate now the best possible route that doesn't stop at that airport. And looking at it, it's at the prediction stage. As you can see, it takes a detour by it actually completely regenerates part of the route by stopping at a different American airport and then a different Canadian airport.
There's a couple of no METAR found.
Yes, so I get the METAR data from aviationweather.gov, and that's the weather reports. That's a website by the US government, and if no METAR is found, it means that their website also can't find a METAR from that. And while METAR weather reports are generated at most airports, they are not generated at every airport.
Will this be factored into the weather challenges bar?
The no METAR found is just ignored by the weather challenges.
Okay. Okay.
So now I'm going to go over to the airline routes page. I'm going to, if you'd prefer to see a different route, I can do that, or I can use the same one.
Let's use the same one.
All right. So at this point, this is the fleet drop-down menu. It is searchable, which is very good because there are 300 airplane types available. And I'm going to use my knowledge of the airlines. I know an airplane that Cathay Pacific flies a lot. And I'm going to do a couple that American Airlines flies, which one of their bases is Miami. So this is now going to start loading the results. This one doesn't give me as frequent updates in the console because there are less stages in the middle. But I'm actually going to change the screen share over there so you can see what that looks like. It just from Flask outputs a list of all the requests, and then I have a bunch more data about each generation or each generator being reported there. So from that large block that just showed up, we can see that a route has been generated. So I'm going to change back over to the website. And you can see this route was considered the best. And some of these examples, you can see departure and arrival are blank. This means that between, for example, this destination, Miami and Minneapolis, multiple airlines fly the same route. So those are left blank so that it doesn't clutter up the screen with extra data. In this case, Delta, American, and US Airways all fly that route. And again, you can do the same thing from the left sidebar. I'm going to uncheck Delta Airlines, which flies both between Miami and Tokyo and Hong Kong. Miami to Minneapolis and Tokyo to Hong Kong. So searching again is going to give, well, based on, in this case, probably the same results, except ignoring Delta's flights there. So this is probably going to take another couple seconds to generate. So if there are any, I will start answering questions.
We use the query to search MySQL. Is there any indexes using? Do you have any indexes?
Currently, no.
No. So I will have a suggestion. So if like you're searching by the stops, or you could just create an index on that column. It will increase the query running time. Actually, make it more efficient. So decrease the running time.
Okay.
Yeah.
That's not a feature that I've come across yet.
You could just create an index from MySQL. Yeah.
And at this point, a new route has been generated. This one does actually take a completely different route, stopping in. Well, that's a problem. It does find a Delta Airlines flight. I'm not sure why that's happening. That hasn't happened in any testing before.
All right, is that it?
Yeah, at this point, I'll
okay.
answer any questions.
Looks good.
All right, so questions. Dr. Wang, do you have any questions?
Yeah, I was about to ask the question on the index, since I already asked that one. So no questions so far. Looks good.
Yeah. Okay. So actually, in the presentation in the DS 420 course, I didn't see this part. I think
Yeah.
it makes this project much more complete. Um, I feel like there are some missing pieces when you are doing the DS 420. I had that impression because you didn't show me this part. So
Okay.
I think with all the optimizations, the root generations you have done in this project, makes it very strong and looks very good. So I did notice that in one of your presentation slides, you had one optimization called caching. Can you elaborate more on that part?
So I haven't really looked into implementing caching, but
Mm-hmm.
one example I was thinking of is that I have that large airport list, and
Mm-hmm.
sometimes in route generation, I send a lot of queries to MySQL, and I want to investigate if it's quicker to find an airport's latitude and longitude by accessing that list. I have a binary search that does that versus sending a query to MySQL every time I have to do that.
I see. Um, you know, in one in the DS 420 course, I actually mentioned about a technique called memcached. That's like a memory caching mechanism. It's a software you can implement to any software. It just caches the results so that you don't need to rerun that part every time when you do this same algorithm. That definitely can be helpful if you want to do the caching layer. But be prepared. Caching can be annoying sometimes as well. Sometimes it will just make your performance even worse because if you don't pay attention to what you're trying to cache, then it takes a lot of memory, but eventually it's gonna kill your performance. So
Mm-hmm.
just be prepared of doing that. Yeah, yeah, and overall I think it's great. I actually it looks to me I don't know if you agree, Dr. Wan. It looks to me as it's beyond the scope of an undergraduate project.
Yes, I'm impressed with what Niklas has done. So it's a very good, I can see a very good result from this project.
Thank you.
Yeah, if only I can be picky, then I would say
Go ahead.
push for the loading time a tiny bit. Um, Using the indexing and caching could be helpful, but I think the most important part would be the algorithm design. I'm not entirely familiar with the algorithm themselves, but looks to me that there's still some room for you to improve if
Definitely.
you even want to push further on the performance part. But yeah, it's amazing for me. I think I'll definitely recommend this to be like a award recipient of the honors project.
Wow, thank you. Yeah,
All right, so yeah, like so the timeline for this is we do have a deadline on 15th for you to submit everything, right? So I think it's time we can now sign the documents if you have them already.
I
Um,
do.
since now we have Dr. Wang and me here in the meeting, then you can possibly just distribute them to us.
Yes, there is a title page that needs to be signed by both of you as
Mm-hmm.
well as Dr. Atwood.
Yeah. Uh,
Um,
by the way, she doesn't need to listen to your presentation. She
okay,
just need to sign it on the paper.
awesome. Um, I just got that email recently. Why can't I find it? There it is. Um, Oh, and there's information that I haven't filled in myself yet on there. But I will send that. Does the Zoom chat? Oh, what am I screen sharing? Okay. Does the Zoom chat support documents being sent?
I guess you could send it on Slack, right?
Slack?
Oh, I don't have
Oh, you don't
that
use
anymore.
Slack, or just
Yeah,
email?
just send to the emails.
Yes, I will email it.
Mhm. I'll ask that one to sign it first, and then I'll sign it and send back.
Okay,
Okay.
then I'll email it to you, Dr. Wang.
Yeah.
And I have too many windows open.
How many screens you have?
3.
Okay, decent. I know Ian had 5, right? I remember.
I thought he said 3.
3?
But
Okay.
Ian's kind of crazy when it comes to computers. I remember in his dorm room freshman year, he was my neighbor, and he had, I think, 3 monitors, 3 computers, and a physical piano-style keyboard.
Wow.
That email has been sent.
Sounds good.
As,
Just before we finish today's meeting, just want to follow up with your plans after graduation. Since now you have done a perfect job in graduating, have you planned anything after this?
I'm going to take a bit of a break because the
That's
last
good.
2,
Yeah,
3, 4 weeks
I
have
know.
been absolutely crazy.
Mm-hmm.
Yeah, Dr. Wang, I mentioned this to Dr. Lee, but I'm actually doing 2 honors in the discipline project this semester. The other one in my German major.
Oh, okay. Very good.
But as soon as I'm ready,
How
I'm
was
going
that
to,
one going?
That one's pretty good. It's a 34-page Word document.
Wow.
Wow.
Half of that is
I know
an
you
English
did that
translation.
during the Thanksgiving break, right?
Yeah, I wrote almost all of it around that time.
Mm-hmm.
Yeah, half of that is an English translation, so it looks like more than it feels.
Okay.
But yeah.
Luckily, now Google Translate did better job than the old days. So
I would not trust Google Translate with that.
Okay.
Yeah, I'm also going to start applying for jobs, specifically in any European country, more or less, because I don't want to live on this continent. And I have a couple ideas for programming projects that might be a bit of fun. I thought of a variant of chess where one of the pawns can act as a queen.
Oh.
And is kind of hidden.
Yeah. Okay. All right. So I know one of my current thesis of advisee. He's doing. His name also Niklas. He's doing a chess AI kind of project. He asked me to be his co-advisor. Kind of interesting. Yeah. All right. So keep going, and if you have time, we'll come back, and I'm welcoming you to any chats if you like.
Yeah, I'll definitely stop by if
anytime.
I'm back in Elizabethtown.
Yeah. All right.
And that's possible to do.
Yeah.
Okay, have a great winter break.
All right, thank you. You
Okay,
too.
great.
Thank you.
Bye-bye.
Bye.
Bye.
Oops.